We will move now into how the tropical circulation gets set up with the heating. So we will relate our verticity balance equation to the heating term and see schematically how the dynamic circulation actually evolves. Remembering our verticity balance equation, we said this additional term occurs at the scale of 10 to the 7 meters, which are the large-scale tropical systems, and the Rossby wave is less than 1 at this scale. Whereas at the in the extratropics and smaller scale systems in the tropics, we had this term drop off, and the balance was very different, just in terms of moving the vortex tubes and generating geostrophic adjustments and so on. In the tropics, we also need at these what people call macro scales. We also have vertical motions created by diabatic heating associated with the convection, and we said when there is positive correlation between W and temperature, then heat gets advected as well, which is critical for setting up the motions in terms of building potential energy, converting to kinetic energy, and so on. Writing this again, the static stability in terms of Brent-Vesala frequency and gravity, and equating that approximately to the heating. Convection and heating, this is what is driving the tropics, right? And the question is to explain the resulting motion without necessarily explaining exactly what drove the convection in the first place. Writing the verticity equation, remembering that d dt of f is 0 and that the planetary verticity is much greater than the relative verticity. We have d zeta dt, the relative verticity, plus beta v. This is df dy, the gradient of Coriolis in the latitudinal direction. So that is the planetary verticity varying with latitude. And this term we will see more soon. That's kind of the planetary verticity advection term. And you have the divergence of the planetary verticity, which can give you these baroclinic processes that we talked about before. We already approximated our continuity equation in terms of horizontal divergence related to the vertical motion. So essentially you have moisture convergence driving vertical motions carrying background densities. This is the so-called Boozeness approximation, which I should have mentioned before actually. You write rho as rho 0 plus delta rho, where delta rho is small compared to rho 0, and when you have 1 over rho, then 1 over rho 0 plus delta rho can be just written as 1 over rho 0. So the density variations in the direction of gravity g are ignored in this case implicitly. Okay, so looking now the balance using the continuity equation and the verticity equation, we are replacing that term. Then we are getting a verticity equation which relates to the vertical motions, and remembering again these relations for a shallow barotropic fluid of depth h. We are back to barotropic because the tropics are nearly barotropic. Then Rossby radius of deformation is the gravity wave speed divided by the Coriolis, so that's square root gh over f. I don't mind repeating these so that you see them again and again and get kind of fixed in the head as far as the concepts is concerned. So this gives us the net equation for how motions are driven by heating in the tropics. Okay, we are creating verticity with planetary advection of planetary verticity by meridional motion and by the heating term. Okay, so the heating term in the tropics can give us advection and verticity variability, which is our dynamics, tropical dynamics. looks simple, but actually interpreting these in the actual dynamics is going to get more complicated. So looking at Rossby radius of deformation here versus latitude for different equivalent depths, as we can expect, when the equivalent depth is very shallow, 20 meters, the Rossby radius of deformation near the equator is basically going to infinity, 1 over f, and then it drops off and is very small at very high latitudes. Basically that means the processes in very shallow waters can be very small scale. As the equivalent depth increases, the Rossby radius increases as well, as we can imagine. But in all cases, as we go to higher latitudes, gravity wave speed and Coriolis give us a combination of very small scales. Basically that means if you are doing modeling, the scales you have to resolve are going to get smaller and smaller as you go to higher latitudes. Okay, this is a schematic diagram showing the response of the tropical atmosphere to deep convective heating that we looked at briefly in the case of geostrophic adjustment. The forcing scale here is greater than 2 pi r, so the mass perturbation is large enough that the winds adjust to the perturbation, as we saw before. Vertical velocity distribution associated with the heating produces vortex tube stretching in the lower troposphere, generating low-level cyclonic verticity. In the northern hemisphere, cyclonic circulation is counterclockwise, and vortex tube shrinking in the upper troposphere, producing anticyclonic verticity and an anticyclonic outflow above the convective heating. So the advection of planetary verticity by resultant flow generates relative verticity that produces a westward propagation of the disturbance, with low-level cyclone moving westward into the region of increasing cyclonic verticity, whereas the upper level anticyclone moves westward into increasingly anticyclonic region. That's a lot of words, but just look at the figure. You have WZ less than 0 because there is vertical motion upward, but it's going to hit 0 at some point, so the gradient is negative. Whereas here you are going from vertical velocity decreasing and the gradient increasing. So you can see the contrast here of downward motion, WZ less than 0, so it's downward and the gradient is increasing. The heating is maximum somewhere in the middle, and it's producing cyclonic verticity below, anticyclonic verticity above, and there are perturbations radiating out into increasing cyclonic verticity here and increasing anticyclonic region here. And there is this broad scale subsidence that we talked about before when we get away from the convection. Whew. Sounds complicated, but stare at these and make sure you can connect the dots in terms of how tropical heating can generate these dynamic circulations in the tropics, which allows us to explain the weak temperature gradients and baroclinic processes, or vortex stretching and coupling of the low level and the upper level in terms of generating circulations. So we have not completely explained away the conundrums, but we are getting closer to consistently explaining the relation between the heating, the vertical motions, and the horizontal motions. This is how the complete structure of the tropics in terms of near barotropic structure, weak temperature gradient, and vertical and horizontal balances can be explained. It is kind of mathematical, but conceptually, physically, it's easier if we don't worry too much about how the convection and the heating got set up in the first place.